All right. We saw that rational functions have two of the key components to them, or the ones that we looked at last time, were the vertical asymptote and the horizontal asymptote. So let's just kind of review that for a second for one of these. Rational functions. 6x plus 8 over negative 2x plus 3. Okay, so we talked about vertical and horizontal asymptotes. All right, so the good thing about a vertical asymptote is it's basically the same every time. How do we find, or when do we know we have a vertical asymptote for one rational function like this? Well, we know it's where the denominator equals 0. We cannot divide a fraction by 0. And so to find our vertical asymptote, yeah, it's generally speaking where the denominator equals 0. So if I set the denominator equal to 0, that identifies for me that particular feature for my rational function. And so that, what does that wind up being here? If we do it this way, subtract 3, divide by negative 2, got x equals 3/2 or 1.5. Okay, and so if I put that on the graph here, the way I can document that or put that on the graph is just put at 1.5 on the x-axis a vertical dotted line. All right, and we'll talk more about what it means for the graph in just a second. But let's go ahead and do also the horizontal asymptote. For the horizontal asymptote, one such as this, we look at dividing. We do a y equals a over b, where a and b are the leading coefficients. A is the leading coefficient of the top, b is the leading coefficient of the bottom. And so in this case, it would be 6x divided by negative 2x. We want to go ahead and put the x on there. The reason this works is because, yeah, the x's will, if we do that, cancel out, and we wind up with 6 divided by negative 2, which is just negative 3. Okay? With me on that. All right, so what we should do with that is, since this is a horizontal asymptote, draw a dotted line for negative 3 on the y-axis, or at negative 3 on the y-axis. And we'll talk about what that means more in just a second. All right? And so that's how we find those parts of, in rational functions like these, we'll have those two types of things. Okay? All right, but that does give me something about the graph, but it really gives me no points to deal with, to work with. And so we are going to talk about a couple other points here, several other points, and one of them are the intercepts, the y-intercepts and the x-intercepts, two other parts, just like we do with the polynomials and the quadratics. We also do want to talk about the intercepts. And the good thing about them is, basically anyway, you do these the same way as we've always done. We haven't done the y-intercepts for these rational functions yet, but we find the y-intercept just like we found the y-intercept before. How do we find the y-intercept? Set x to 0, okay? All right, so that'll give me y equals x to 0 well, that's 0, so that gives me 8 over 3. If you divide 8 by 3, you get 2.6666, right? 2.7 basically, approximately. Okay. What about the x-intercept? Well, the x-intercept, we set y to be 0. But in this case, we have f of x is 0. Instead of y, we have f of x. So set f of x equal to 0. Now, this type of equation maybe we haven't talked about yet, but easy enough to solve that. To solve that, just multiply. One way you can think of it is just multiply both sides by this negative 2x plus 3, the bottom. And here's what happens. Nice things happen because, well, the reason we multiplied is so it'll cancel out over there, and just we'll have on the right side here 6x plus 8. Now, what's 0 times anything? 0 times anything is 0, so this side is just still 0, you see. So really it just amounts to being 6x plus 8 equals 0. That's going to be our x-intercept. So if I subtract 8, I get negative 8 equals 6x divided by 6. I get that's negative 8, 6 equals x. Of course, that reduces by 2. That's negative 4/3 is x. X-intercept, which is about, what was that, negative 1 1/3? All right, so negative 1 1/3 x-intercept. Okay, so that gives me some limited information. Does give me some information, but it is kind of limited. All right, so we said the y-intercept, let's go ahead and put it up here, is 2.7. So it crosses the y-axis at 2.7, and then it crosses the x-axis over here at negative 1 1/3, negative 1.333 if you want to. You're right about there, wouldn't it? That's where it crosses the x-axis. With me on that. All right. Still, though, just some limited information. What I'd like for us to do also with these rational functions is do a little bit of a table here. And on my table, what I'm going to do are some x values, choose some x values and find the point for those x values of values around the vertical asymptote. Just get some values on your table around the vertical asymptote, where the vertical asymptote here is what? 1.5 in this case. Okay, and so some good values around x is 1.5. Well, x equals 1 would be a good. And what I mean by around, do at least 1 point on either side. And I would probably say if you don't have any, like on this case, I don't have any points on the right side there of the vertical asymptote, so I'd get probably a couple of points on the other side of the vertical asymptote. So in this case, I'm going to do x is 2 and x is 3. That would give me a point on the left of the vertical asymptote, and then these would be on the right. So a point on the left and 2 points on the right, since I don't have any points otherwise on the right. Okay? With me there. All right, so let's see what happens. If x is 1, we're going back to this, so the y would be, x is 1, so it would be 6 plus 8 6 times 1 plus 8 over negative 2 times 1 plus 3. Well, that's going to be 6 plus 8 will be 14. Negative 2 plus 1, negative 2 plus 3, that'd be 1, wouldn't it? So that's 14. So when x is 1, I get the y value to be 14. When x is 2, do the same thing. X is 2, so I have 6 times 2 plus 8 over negative 2 times 2 plus 4. That's 12 plus 8, that's 20. Negative 2 times, whoops, that's plus 3. Negative 2 times 2 plus 3, what does that give me? Well, that's negative 4 plus 3, negative 1. That's negative 20. So at 2, I'm at negative 20. And then at x is 3, what do I got? Well, I'd have 6 times 3 plus 8 over negative 2 times 3 plus 3. Well, that's 18 plus 8, that's 26. Negative 6 plus 3, that's negative 3. Okay, so that's not as nice a number, but it's 26 divided by negative 3. It's negative, what would be negative 8.66666? Say negative 8.7. Is that right? 26 divided by negative 3 is about negative 8.7. With me on that? All right. So let's go ahead and graph those points. Is that okay? Is that one right? Did anybody check me on that? 26 divided by negative 3 is negative 8.7. Okay? Nobody's checked me. All right. We'll go with it then. All right, 114. Okay, so at 1, I'm at 14. That's way up here. And so that is on this side of the dotted line, but it's at 14. Then at 2, I'm at negative 20. So let me drop that down a little more. So at 2, I'm way down here at negative 20. So it's right about there. But note it's on the other side there of the vertical asymptote, the vertical line. Then at 3, I'm negative 8.7. 4, so let's say that's negative 8, and that's negative 9, so it's about right about there. With me? Okay. So again, that's limited information, but I think with what we know about vertical asymptotes and things like that, we can get, and horizontal asymptotes, we can get this. All right, so let's connect the dots. And we'll kind of do this in two pieces because basically the vertical asymptote divides it into two parts. So let's do the part to the left of the vertical asymptote here. So connect the dots. All right, so going back to what we saw on the graph previously of my on the handout that I gave you, what we saw was either on either side of your vertical asymptote, either your graph will go upward without touching that vertical asymptote, or it will go downward without touching the vertical asymptote. And as it appears, on the left side of the vertical asymptote, since these points connect up here, it looks like it's going upward, doesn't it? So that graph is going to go towards that vertical asymptote, but it won't touch it. So it will continue going upward there towards that vertical asymptote. All right? Now let's go to the other side here, and then we still have a little bit, but what does it look like is happening on the right side of the vertical asymptote? Well, these points connect up like this, so it looks like this is going downward towards the vertical asymptote. So one side's up, the other side's down at that vertical asymptote. That will always be how it works for a vertical asymptote. Okay? However, that leaves two other parts here, and that is on the ends. What we saw happening on the ends of the one we did on the handout was it levels out. And where does it level out? It levels out at the horizontal asymptote, doesn't it? So this is going to level off on the ends at the horizontal asymptote. So back to the left side here, if I connect the dots here, if it's leveling off here, doesn't this have to level off, come out here and do my little leveling off? And then over here, it's on the Over here, it comes up, and then it levels off on the ends at the horizontal asymptote like that. So the ends will always level off at your horizontal asymptote on both sides for ones like this. That's the way a rational function of this sort works. No, they don't. They level off, and they get closer and closer to it. Sometimes it can cross the horizontal asymptote, but usually not. But it just kind of levels off there. I mean, it gets real close, like it does here. It gets real close to that, but it just kind of levels off on this side. Okay? That's how these rational functions like this operate. All right? All right. Let's do another one. These are all about the same here. This one's, though, got a little bit of difference. All right, let's say we've got f of x equals 8 over x plus 4. Okay, so starting with the vertical asymptote again. What do you got there? Vertical asymptote, always pretty much the same. Set denominator equals 0. We got x plus 4 equals 0, so that's going to mean the x equals negative 4 is the vertical asymptote. All right, and so over here for vertical asymptote, we're just going to draw that in as a vertical straight up and down line. All right, the horizontal. Well, if we have the same degree on the top and the bottom, numerator and denominator are the same degree, we do y equals a over b. However, as this is, are the degrees the same? That is, the x power is the same here as it is here? No. No, I don't. I don't have an x term up here. I just have the constant. And so, and the degree 1 here, so the degree of the bottom is 1, the degree of the top we would say is 0 because it doesn't have an x term. So the degrees aren't the same. So there's a couple ways we can do that. If you think about it, we could say this is 0x plus 8 over x plus 4. We could do that and say, then we could do 0x divided by 1x, and we get y equals 0. Or it's going to be the same anytime we have that. If the degree of the numerator is less than the degree of the denominator, like we have here, then you're always going to get 0. This is kind of the way the book does it. If you see it that way, that's fine. But if you see it as, the degree of the numerator is less than the degree of the denominator, it's always y equals 0. That's a horizontal asymptote. Either way you go, you get y equals 0. So over here, I would dot in what? Y equals 0. What's y equals 0? Where's y equals 0? Well, y equals 0 is right on the x-axis, isn't it? So the dotted line is the x-axis, horizontal dotted line. Okay, all right, so that's a horizontal. What else did we do? Well, we got some other things. Let's talk about the intercepts. The y-intercept, easy, x equals 0. That's 8 divided by 4. That's y-intercept is going to be 2. The x-intercept, we have a little bit of trickiness there. The x-intercept, we set y, which in this case is f of x, to 0, which gives me one of those equations like we had a while ago. Multiply both sides by x plus 4 to get rid of the x plus 4 on the right. So the x plus 4s on the right cancel. 0 times anything is 0, so we get 0 equals 8. What about that? 0 equals 8. What's the x-intercept? Well, that doesn't make sense. 0 does not equal negative 8, so there's no solution to that equation, so that means, what's the x-intercept? There's no x-intercept. So this one is not going to have an x-intercept because there's no solution to that x-intercept equation. With me? Okay, so let's put the y-intercept up here at 2. Okay? All right, that leads us to our last calculation thing, and that is a table. And again, the table, what I want on the table are x values around your vertical asymptote. And to be specific, let me just go ahead and get 2 x values. So x values around the vertical asymptote. And to make it real specific for you, let's get 2 values on the left and 2 values on the right of the vertical asymptote. And those will give you some good points to graph this thing. Okay? 2 values on the left of the vertical asymptote, 2 values on the right. All right, so what would be 2 x values on the left here of the vertical asymptote? The vertical asymptote is here, -4, so how about -5 and -6? And then 2 values on the right, how about -3 and -2? Okay? 2 values on the left, 2 values on the right of the vertical asymptote. Okay, so we're just plugging in those x values to get the y values, plugging in over here. All right, so if x is -5, we've got y equals 8 over -5 plus 4. That gives me 8 divided by -1, which is -8. Okay? If x is -6, I'll have y is 8 divided by -6 plus 4. That is 8 divided by -2. That's -4. For -3, it'd be 8 divided by -3 plus 4. Hey, that's 8 divided by 1. That's +8. And then x is -2. We'll have 8 divided by -2 plus 4. That is 8 divided by 2, which is +4. Okay? All right. So, plot those out. -5, -8. -5, -8, right there. -6, -4. So at -6, I'm at -4. Right there. At -3, I'm at +8. -3, I'm at +8. And at -2, I'm at +4. Right there. Okay. So again, I didn't write it down. Maybe I should write it down. All right. So at the vertical asymptote, the graph will either go up or it will go down at the vertical asymptote. So, and that's on either side. At the vertical asymptote, the graph will either go up on the left, up or down on the left, and then up or down on the right. That's our 2 choices. And it may, we've seen them both, one, they've alternated, but they could both go up. The left could go up, the right could go up also. Both could go down. A lot of times they alternate. One will go down, one will go up. What have I got here? Well, if I go to the left, these 2 points connect up. It appears they do what? Headed downward, right? So at the vertical asymptote, we're headed downward on the left, and then at the vertical asymptote, to the right of the vertical asymptote, looks like it heads up. With me? Now again, the reason that happens, why we've got a disconnection there, if you will, the graph doesn't connect up, these points don't connect up, is because of the way the vertical asymptote is formed. We have a vertical asymptote when the denominator equals 0. And that's because we don't have a value. If I set x to be -4, I have 8 divided by 0, that's undefined. So the graph cannot cross this vertical asymptote. That's another component here. It either goes up or down at but it doesn't cross the vertical asymptote. So that's why we get sort of this action here. Okay? What does that leave us? The rest. Well, what about the ends? When I wrote that down, what happens at the ends on a rational function? It levels off. Where does it level off for these? Where does it level off at? Horizontal asymptote. Okay? And so the horizontal asymptote, so it levels off on the ends at the horizontal asymptote for both ends. Once again, write that down. Okay. All right, so this graph, if I continue for the ends here, this point, then it's going to come up and level off. Horizontal asymptote 0 here. Same thing over here. Well, I forgot to connect that point, but then it's going to come out here and level off at the horizontal asymptote. Okay? We'll always, for these, we'll always do that. Okay?